So last time we got into chapter 4, and we really talked about the atom there. And we talked about a number of experiments that led to sort of the understanding of the atom. And really it's three subatomic particles, which are protons. That way, there you go, protons, which are positively charged. We have electrons, which are negatively charged, and we have neutrons, which have no charge. And we talked about some experiments. A lot of this sort of understanding of electrons was done through the use of the CRT, or cathode ray tube, the understanding of sort of its mass of an electron. From those early experiments, remember we had sort of a early model of the atom, which was a plum pudding model, where it was thought that most of the atom was pretty much positive charge, really spread out all over the sphere of it. It had these negatively charged electrons embedded inside of it. And the sort of early model here said that most of the mass of the atom was that of the electrons. Now, this is sort of the accepted model till, as we talked about, really the big experiment happened by a guy named Rutherford. He did the gold foil experiment, and that was Rutherford. And again, he shot at these alpha particles, which are radioactive, positively charged particles, at basically pieces of gold foil, or atoms, essentially. And again, as we talked about, he sort of expected, because they're heavy and moving really fast, for them to sort of go through and sort of be deflected a little bit as they sort of punch through that positive smear, if you will, over the atom. Obviously, as we also talked about, things with the same type of charge don't like to be near each other, right? And things with opposite charges are attracted to each other. So a positive charged alpha particle shot at that positive sphere should be able to punch through, because it's heavy and moving fast, with a little bit of deflection as it goes through there. What they actually saw was pretty much the alpha particles didn't have really too much trouble. Most of them went through with really no deflection. But they did see every now and then, again, these alpha particles were sort of scattered at really large angles, maybe even came back to where they're shot at. And as we talked about, what that really meant was they did have to sort of abandon the early model of the atom there and come up with sort of a new model based off of what Rutherford discovered. And the idea here is what those alpha particles hit was a really densely positive core, and that's what's known as the nucleus. And it was sort of discovered that in our nucleus, that is where we have our protons and our neutrons, and again, our protons being positively charged. And in that empty space where those particles really didn't have any trouble and they kind of sailed by with no problem, that is where we find our electrons, again, pretty much randomly moving about the nucleus. Again, as we talked about, there will be some attraction between the electrons and the nucleus, because electrons are negatively charged, and the nucleus there is ultimately positively charged, even though it also has neutrons in it. But the only thing that has a charge in the nucleus is the protons, which are positively charged. So that's essentially what kind of keeps electrons around, so they just don't kind of sell off and fly around. There is some type of attraction to the nucleus that keeps them from just, all of them just leaving. Yeah. Yeah, so everything sort of in chemistry, in a sense, no matter what you do, there's always going to be situations where you will have things that have similar type of charges that come together. So for example, if you think about something like sodium chloride, which is a salt. So when that's in a solid state, it aligns itself in a way where there's positive ions and negative ions near each other, but there's also going to be positive guys near each other and negative guys near each other. So ultimately what most things try to do is they really, as weird as it sounds, try to kind of move around and kind of get as comfortable as they can, where they sort of maximize attractive type forces and minimize our repulsion forces. And ultimately, as you'll talk a little bit when we get to bonding, that's kind of the idea. What happens in bonding is, the goal of almost a lot of things that happen in chemistry is to kind of minimize the amount of energy and make it sort of a more stable state of energy. And that's what things do. They really do sort of vibrate around until they kind of find, okay, well, I'm kind of okay in this situation. But there will always be in all situations a place where, you know, you'll have similar charges near each other, but they will try to sort of adapt themselves in a way that they can kind of live with it, essentially what happens. Yeah. Other questions? Okay. Now, in terms of this, this is really sort of the modern version of the atom. Also remember that the other major difference is the nucleus is again where most of the mass of the atom is from. And that's because a proton and a neutron, they're very similar in the masses of each of those particles. But it is actually, as we talked about, the neutron that is slightly heavier than the proton. And the neutron is the heaviest out of all of them. And the proton and neutron is about 1,800 or so times heavier than an electron. So our nucleus, which contains both protons and neutrons, would make up most of the mass of the atom, as electrons are much, much lighter than any of those particles that we would find in there. We talked about afterwards a couple other important aspects of it, which is our atomic number. And again, that is the number of protons there are in an atom. The mass number, which is the number of protons plus the number of neutrons. Remember that on the periodic table, you can find the atomic number, but you cannot find the mass number, as we talked about. And again, when you calculate anything that is a mass number, atomic number, the number of protons, electrons, or neutrons, they all have to be positive whole numbers. And again, as we talked about, very commonly misused is the number on the bottom, the symbol, which is the atomic mass, which we'll talk a little bit about today. But it is not the mass number. So remember, they do need to be whole numbers, and you will have enough information given to you that you'll be able to sort of calculate all those things in these type of problems. We do write symbols for isotopes. If you remember, isotopes are really the same element, but they have different masses, and that's because they contain different numbers of neutrons. And when we do it, we do the symbol there on the right, and then we do atomic number. Not there. We do the atomic number on the bottom. Seems like a better place for it. Yeah. And up on top there, we do the mass number. So up on top here, mass number. So like copper 6429. Yeah. So 64 mass number, 29 atomic number. If you subtract the two, gives you the number of neutrons. So if you take the top number minus the bottom number, that will give you the number of neutrons. Also, if it's written like this, that number again is the mass number. Out of all three of those subatomic particles, as we talked about, the one that is the most important in terms of, thank you, the most important in terms of what element you're dealing with is which one? It is the atomic number and the number of protons. So again, if you look at the periodic table, no element has the same atomic number. So if you know the atomic number, which is the number of protons, you know what element you're dealing with, and vice versa. If you know the element you're dealing with and you want to know how many protons it has, all you have to do is go find it on the periodic table and find the atomic number, and it will tell you obviously the number of protons that there is. Any questions on any of that stuff there we talked about last time? I think that's where we laid it up, if I'm not mistaken. So I don't think we did this example, right? We stopped right at this one. Yeah. So why don't we do this example? So for with our mass number and our atomic number. So once again, it is the number there on top. That is the mass number. And it is the number on the bottom there. That is the atomic number. And the other thing we talked about was symbols for elements, right? And as we can see here, these are some examples of symbols. And as we talked about, if it's a two-letter symbol, we want to capitalize the first one and lowercase the second letter. And obviously, if it's a one letter like the last one there, we just capitalize it. So CO is cobalt. And we know from the atomic number, right, that the number of protons in cobalt here would be 27, basically positive guys. to match the atomic number that we see. We also know, or if you don't know, this is going to be neutral, as we do not see anything written right about there, which is typically where a charge would be if it did have a charge. So it is safe to assume that is neutral. So the other thing that we talked about is the atomic number's definition is the number of protons, but if it is neutral, then we should have how many electrons in this case? We should have an equal number of electrons to balance out the charge. So we would have, in this case, because it is neutral, 27 negative electrons, which really gives us the overall charge of 0. So again, that's why it is neutral. Also a reminder, as we talked about last time, if you're asked what is the definition of atomic number, it is only protons. So sometimes people think it's protons and electrons, and that's not the case. It's only the number of protons is the actual definition of atomic number. But again, it will tell you the number of electrons if we're dealing with something that is neutral. For our number of neutrons, we're going to take our mass number minus our atomic number. How about a 33 there? That sounds like a winner, I hope. Any questions on any of those there? By the way, the other thing we also talked about was all elements have protons, electrons, and neutrons except for hydrogen. Hydrogen, again, only has a proton and an electron, does not have a neutron. Again, all other ones have all of them. We're going to look at the next one, which is Cl. So that's our friend chlorine. Looking at the atomic number, which is our bottom left. Our number of protons in this case will be 17. Once again, there is no charge on that thing, which means we should have a matching number of electrons to balance out the charge, as frankly, protons are positively charged, electrons are negatively charged, and neutrons have no charge. So these are really the only things that can change the charge, right, are these guys. In this case, for our number of neutrons, once again, we're going to take our mass number minus our atomic number, 20 in that particular case. Any question on that one there? Coming down here, U is uranium. It's on the bottom. We don't deal too much with it. It is radioactive, but that is what that means. Again, we see no charge. We will again look to the atomic number here to give us our number of protons, which will be 92. And using our same logic as we did for the other, since there is no charge, again, we will need a matching number of electrons to give us, again, an overall charge of 0, basically. Our number of neutrons in this case, taking our mass number 238 minus our atomic number, which is 92, feels like a big number, $146 maybe, I don't know, give or take, we'll go with that. 146 neutrons are there. Again, all these numbers, as we see, are all whole numbers. Yes, no decimals. We didn't go to the periodic table to grab any number on the bottom there. The only number we should grab is the protons from the periodic table if you needed to. Any questions on how we got to any of those there? All right, then why don't we try writing some symbols? Why don't you write the symbols for each of these with both the mass number and the atomic number? If you have a periodic table, it might be helpful. Or if you have really good eyes, that one might be helpful. I'm not sure. I'm standing underneath it and I can't see it, but. Okay, so let's take a look. We'll start with krypton. Clearly, your periodic table is your friend when you're doing this. So we would go to the periodic table. We would find krypton, which is Kr. That would be our symbol. Again, capital K, lowercase r in this case. Once again, from the periodic table, we can find our atomic number, which would be the number on top. And that should go bottom left of our symbol, right? The top number is the mass number, which we do not have at this point. We actually have to calculate what the mass number is. And again, the mass number going to be our number of protons plus the number of neutrons. From the periodic table, our atomic number tells us it is 36 protons. And in the problem, it tells us it is 48 neutrons. That's an 84, I believe, and that would get us right about there. Yes, this guy would have obviously 36 protons. It would also have 36 electrons. You could assume it's neutral since it didn't say anything about a charge. And obviously it has the 48 neutrons. Any questions on that one there? Doing the same thing here for nitrogen. Again, we would go to the periodic table. We would find nitrogen, which is N is the symbol. Again, the important information we could pull from the periodic table there is going to be our atomic number, which is our number on top. And for our symbol, it does go on the bottom. That tells us that nitrogen here has 7 protons. We can see in the problem here it has 6 neutrons. So our mass number will just be adding those together, 6 plus 7, 13, I think. And we'll have a symbol that looks something like that there. Any questions on that one? Lastly here, we got iron, and iron symbol is Fe. Once again, we could get 26 as our atomic number, which will go on the bottom. And in this case, they actually gave us the mass number, which is 56, which should go up on top. And in this case, we're looking for also how many protons, electrons, and neutrons. So in this particular case, the number of protons would be our atomic number, which is 26. It is neutral in this case, which means, as we've been talking about, we should have the exact same number of electrons to balance out the charge to 0. And our number of neutrons here will be calculated the same way as normal. Mass number 56 minus atomic number 26 gets us about 30 neutrons in this case. Any questions on mass number, atomic number, protons, electrons, neutrons? Mass number is, the definition of mass number is really the number of protons and neutrons there are in an atom. The atomic mass is actually a average value, as we'll talk about in just a second, actually in this chapter, but it's really an average value of all the naturally occurring isotopes, their masses, and a calculation that was done to calculate those. And again, what confuses people a lot of times is, again, those numbers oftentimes are very close to one another. So they actually are different things, but they are based kind of on some of the same things because they're based on the mass, obviously, of protons, electrons, and neutrons, but they technically are 2 different things. Other questions? So let's say we had something with charges, right? That could happen. It's chemistry, you never know. So let's just say we did have something with charges. Let me get a little room here. I think I'll get rid of my krypton here. All right, so let's say we end up with something that does have a charge. And by the way, those things are what are referred to as ions. And these are things that have charges. And there's really 2 types of ions that we come across here in chemistry. And that is our friend, the cation. And the cation are things that have positive charges. And there are anions, which have negative charges. Now, let's say, for example, we'll borrow the nitrogen that we got going on there in the middle. Let's say we have this nitrogen. We'll go with the same numbers there, 13 and 7. And let's give it a -3 charge in this particular case. So how does this affect sort of what we were looking at, our protons, electrons, and neutrons? Let's start with the number of protons it should have. How many protons should this guy have? It is still 7, right? And that is because if I change the number of protons, it's no longer nitrogen, right? So we cannot do that. So clearly the charge is not made by changing the protons, and neutrons have no charge, which means that's not going to do much. So it really is the electrons and the changing of the number of electrons that you got going on, which is really what creates the charge when something gains either a positive charge or a negative charge. And in terms of the neutrons here, we can still see the number of neutrons would be 13 minus 7. which again, in this example, is the same 6 that we had in our neutral guy. So that means that the number of electrons actually does change. How many electrons should this guy have that has a -3 charge? It would actually be 10 electrons in this case. Because if I take 10 negative things, right, and add 7 positive things to it, I got how many negatives left over? 3. Yeah, I got 3 negative things, which is where that charge comes from. And it's because nitrogen with a -3 charge, which is known as nitride, versus neutral nitrogen on the bottom. Neutral nitrogen on the bottom here has 7 protons, and it would have 7 electrons, right? Like that, electron. So it has 7 protons and 7 electrons, which is why it bounces out to no charge. And in this case, the guy with the -3 charge actually has more electrons than the neutral guy. And again, that means it has more electrons than protons, which is why it has a net negative charge. Yeah. How I got 10 electrons, is that what you're asking? Yeah, I got 10 electrons because it's got to have for sure 7 protons, right? So this guy's got to keep only 7 protons. So I'll just put positive charges like this. 1, 2, 3, 4, 5, 6. So it's got 7 positive charges in there. It can't have any more or any less, otherwise it will no longer be basically nitrogen, right? So every time we put an electron in there, right, a positive and negative basically cancel each other out to 0, right? So you got +1, -1. So if I lay down 7 electrons in there, like I have going on with my neutral guy, all the positive charge cancels out, right? And now we're at 0 charge, which is basically what is in the middle there, right? Where it has no charge. But in this case, if I continue to put 3 more electrons, and now we'll have 3 electrons left over, and each electron's -1, and that would give it a -3 overall charge, which is where the -3 charge comes from. If I had only, for example, sometimes people think, well, maybe it should have only 4 electrons, right? It has 3, so we take away 3 to get the 4. So if we do kind of the same little math there, we have our 7 protons, but if we go the other way and only do 4 electrons, that's only going to take care of those. And that's going to would leave me what type of charge left over? +3, which is not what we got going on in this case. So the reason it has a negative charge is because when you compare it from the neutral guy to the one with a charge, the guy with the negative charge has more electrons, and that's what the negative implies. So whenever you see a negative charge on something, it means that that substance or species has gained more electrons, because it now will have more electrons than it has protons, and that's why it has, again, that net negative charge that's basically flying around. The actual number that you see on the charge is actually how many electrons it gained, right? So it has a -3 charge. It gained 3 more electrons than it had in its neutral thing. And so when you see a negative charge, gained electrons, and the number of the negative charge is how many electrons it gained from its neutral self. And that's a question on that. This is an anion, which again is basically made by gaining electrons in this case. Yeah. Now, if we took the iron on the bottom, and here we already seen it has no charge, and it will have 26 protons and 26 electrons to balance out the charge. If we took the same sort of guy here, 56, 26, and let's give this guy a +2 charge. The number of protons in this case is going to still be 26, which is its atomic number. Again, that cannot change. Otherwise, it is no longer iron. So we're locked into that in terms of positive charge. The number of neutrons in this case would be 56 minus 26, which is 30, just like it was down here. But now it again is the number of electrons that change. And in this case, how many electrons would I have or would I need to end up with a positive 2 charge? It would be 24. So if you take 26 positive things and you have 24 negative things, only 24 of those 26 are going to cancel. And that's going to leave you 2 positive guys left over, which is where the positive 2 charge comes from. And the reason in this case is when we compare the iron here with the +2 charge to the iron that has no charge, which one actually has more electrons? The one with no charge, right? It's got 26 electrons, right? This one has 24 electrons, which means when it became positively 2 charged, it actually lost 2 electrons. And that's what the positive sign means when you see an ion that has a positive charge. It means it has lost electrons. And just like the other, the number tells you how many electrons it lost. So +2 means it laid up 2 electrons or lost 2 electrons from its neutral self. And that is why it actually does have a positive charge, because what we have now is this guy with a +2 charge has more protons than electrons. So it has more positive charge in that atom or ion than it did originally, right? Because originally it balanced out nicely. We lost a couple of electrons and now it has a positive charge. So that is how a cation is formed. You basically will lose electrons. So when you lose electrons, you become positively charged. And the end result of that is you have more protons than electrons. And that's why you end up with a positive charge. And if you become negatively charged, you gained electrons, which is why you are negatively charged, because you end up with more negatively charged electrons than protons positively charged that you started with. Why it's important to maybe just know that +2 means plus I lost electrons, 2 I lost 2 electrons is if I know the neutral guy atomic number, right? And if it's neutral, it will have the same number of electrons. So simply I just need to subtract off 2 from the atomic number and I will know how many electrons that I have. Same thing up here with the nitrogen. I know negative means it gained electrons and 3 means it gained 3 electrons. And I know in the neutral guy, it has 7 protons and 7 electrons. So I could just add 3 to that number and I will get my number of electrons. So when something gains a charge, which happens when metals and nonmetals hook up together, those that lose electrons become positively charged and those that gain electrons become negatively charged. Any questions on that there? All right, why don't you try a couple here? Let's see. Let's do let's do 3617 Cl minus number of protons, number of electrons, number of neutrons in this guy. And let us do aluminum +3. And we'll do 13. Yeah, we'll do 29. Also number of protons, electrons, neutrons in each of those. Yeah, I'm sorry. Yeah. Yes, I think so. You got to memorize the entire periodic table. That's the first exam. Let's all go drop together. No, I'm kidding. No, I'm kidding, by the way. Don't send me an email. I'm just kidding. I'm kidding. Joke, laugh, relax, breathe. It's okay. Life will go on. Although I did know a teacher that was their final exam they gave to their class. It was like an empty periodic table and it's like fill in everything, you know. That's pretty tough. I don't know. I would probably fail myself. Yeah, so you will be. Okay, let's take a look and see. We'll start with the first one here. And again, we definitely know our atomic number there is on the bottom. And that's important because, again, that will tell us the number of protons in this case is going to be 17. We also could get the number of neutrons by taking the top number, which is the mass number, minus the bottom number. 19. Sounds good. I tried without the calculator. That was good. All right. Now we're to electrons. So first off, if we look at it, I see -1 charge. Yes. Did it lose or gain electrons? It gained, right? That's what the negative means. And it also gained 1 electron. That's what the -1 charge means. Usually if it's a 1, we don't write the number next to it for 1. So what we know, though, if we could just think about it logically, is chlorine with no charge would have 17 protons, right? And 17 electrons, right? Based on the atomic number. So if I know it gained 1, that means that this guy would have number of electrons 18 in this case. That would give us 17 positive protons, 18 negative electrons, which gives us a net of really 1 negative electron, which is where the charge comes from. Yeah. Any questions on that there? All right, look at the bottom one there. That's aluminum. We got 13 for our atomic number, which means we got 13 protons. Neutrons here, once again, going to take 29, which is our mass number, minus 13, 16. Sounds good. And again, here we could just analyze what we're looking at. So I see a plus charge, which means it has lost electrons, right? And the 3 means it has lost 3 electrons. And again, if you just want to keep it simple, I know aluminum has 13 protons when it's neutral and also has 13 electrons when it's neutral. And that means that if this guy lost 3 electrons, he should only have 10 left over, right? So 13 positives, 10 negatives gives you 3 extra protons that have a positive charge. And that is where our positive 3 comes from. Any questions on protons, electrons, neutrons, with things with charges? Yes. All right, so clearly you need to be able to identify all those things: protons, electrons, neutrons, mass number, atomic number, and so forth there. All right, so as we've been talking about, isotopes are really things that have different numbers of neutrons. The good news is really neutrons don't usually partake in normal chemical reactions. And that means that isotopes are very used to some people's advantage because they will really perform the same chemistry as other isotopes. And a lot of isotopes are radioactive isotopes, which makes it really helpful in a laboratory situation. For example, if you want to know what happens with copper in the body or in a pathway or something like that, you can use a radioactive version of copper, and you basically could just follow the radioactivity. You'll know exactly where all the copper ends up, and it's very useful. The radioactive version of copper and the non-radioactive version of copper will do the same chemistry because it's all about electrons and those type of stuff. So it's very useful to use radioactive versions, for example, of elements to sort of do some experiments. So the next thing we're going to talk about is chemical composition, which is atomic mass. And that is our friend, the other number that we see on the bottom there of the periodic table. So once again, if we look at carbon, we got 1201. If we look at hydrogen, we got like 1.008. These are the atomic masses. And one of the fundamental properties of an atom is its mass, but obviously it's very small, which means you can't just pick it up and put it on a balance and weigh it or anything like that. So most of the time in chemistry or in science, when we can't necessarily measure something directly, a lot of times what we will do is choose something to use as sort of a standard to kind of compare everybody to. And sometimes we may actually know what the standard is in terms of maybe his mass or something like that. Or sometimes people will just go, we're just going to give this guy a value of 0 or something, and then kind of compare everybody else to it. So when we talk about atomic masses, it's actually an isotope of carbon that was used as the standard to sort of compare everybody to. And it was the carbon-12 isotope was used as the standard one to compare and figure out really the atomic masses of everybody. And the carbon-12 isotope has a mass of exactly 12, what is referred to as 12 AMU, and that is atomic mass units. So this isotope of carbon was used to compare everybody else to. It has this exact mass of like 12.00 AMU. And for example, they did experiments which show that hydrogen is only about 8.4% as big as, say, the carbon-12 isotope. So basically, they did a math, and this is 8.4% converted into a decimal, divide by 100 or move the decimal place 2 places to the left, times the atomic mass there of carbon-12, and we get 1.008 AMU, which is the number that we see on the periodic table underneath hydrogen. Now, when we take a number like that, for example, and you could look at oxygen, which is 16, iron, which is 5585, a couple of things when we do sort of pull that number off the periodic table, we typically go to 4 significant figures. So usually when you kind of pull that number off the periodic table, and depending on the periodic table that you're looking at, you may have a lot more numbers, you may have less numbers written there. But typically speaking, when you kind of pull that number off of the periodic table, 4 significant figures is typically what you go with. Now, when we pull something, say, like hydrogen, which again has 1.008 written there, what that basically means is there's 1.008 AMU in an atom, is one sort of units of atomic mass. Although outside of this chapter, we probably won't use AMU ever. We will use the real more useful unit for us, which is grams per mole, but it comes in a later chapter. But AMU is sometimes used as well. And sometimes we pull that number off the periodic table, and it's what's known as the molar mass, where we use them as grams rather than AMU. It's actually the same number, but it's some different units. When we pull that off, again, 4 significant figures is typically what you want to use, which is why if you look at something like maybe oxygen, it's probably like 15.99999 or something like that, depending on your periodic table. So we do round and stuff like that. Now, when we do look at the periodic table and we do look at carbon, it does say 12.01, which might be strange if the standard that we use is the carbon-12 that has a mass of 12, basically AMU. And the reason that number is actually different is because what we actually see on the periodic table is what is usually referred to, but not by many people, but it really is the average atomic mass. And what that means is the average atomic mass of all the naturally occurring isotopes for that particular element. So something like carbon has 2 isotopes, like carbon-12 isotope, which has a mass of 12, and a carbon-13 isotope, which has a mass of about 13. So it's actually the average value of those naturally occurring isotopes, and that's how they get to the 12.01 number, and that's how they get to all the numbers that you see on the bottom, which again is why they are atomic masses and not mass numbers, because you get a lot of decimals going on there. To calculate that, by the way, you would use this formula here if you were asked to calculate the atomic mass of an element based on some isotopes. You would take the atomic mass in AMU would be equal to the percent of the first isotope times the atomic mass of the first isotope. And by percent, what this is referring to is sometimes referred to as percent abundance or relative abundance. It is basically like the percentage out of 100 of how often that isotope occurs naturally in sort of society. So for example, carbon, one of them is about 90 some odd percent of the time you get that isotope, and you get 1% the other time, or less than that the other time. So that is what the percent abundance is. You then would actually add it to the percentage of the second isotope times the atomic mass of the second isotope. And if you had 3 naturally occurring isotopes, you would just keep following that pattern of taking the percentage times the atomic mass of each of the individual isotopes. So in the example of carbon, we would take the percentage that carbon-12 occurs times 12 for the mass of carbon-12, and we would take the percentage that carbon-13 occurs and times it by the mass of the carbon-13 isotope. If you have all the naturally occurring isotopes there, what percentage should it add up to? 100%. Yeah. So if you happen to be missing a percentage for an isotope, but you know this guy is 50% and the next isotope's 30%, you have one more isotope, right? So 50 and 30 is 80, minus 100 is the other one occurs about 20% of the time. So that is, you know, what you want to think about. So if we look at something here like our carbon, here is carbon-12 and the mass of the carbon-12 isotope. As I mentioned before, this is how often it occurs. Almost about 99% of the time, you'll find a carbon-12 isotope flying around. And we also have a carbon-13 isotope, which has a mass of about 13 or so. And that occurs about 1.1% of the time. So we could do our calculation to calculate the atomic mass. We would take the, as it is written above, but let's just talk about a couple of things in this calculation. I would take the percentage of my first isotope. When I'm going to multiply by a percentage, I need to convert it into a decimal, right? So you can divide that by 100, or you can move the decimal place 2 places to the left. But what you should be punching into your calculator is 0.9897. That is 98% converted into a decimal. You divide by 100, we'll get that for you if you're not sure. We're going to times it by, again, the atomic mass of our first isotope. So this is basically our carbon-12's isotope mass. The other thing that people always want to do is like multiply or other things. It is actually adding is the next thing that you would do for the next isotope. And again, if I take our second isotope that we got going on there, that's 1.11%. Again, you can either move the decimal or just go 1.11% divided by 100%, and it will do it for you. And times it by 13.003 AMU. And that would represent our carbon-13 isotope. So these are the naturally occurring isotopes of carbon. When you do the math there, we're going to get this number here, hopefully. We'll trust our calculation. And that is the number that you see on the periodic table right underneath carbon, which is 12.01. It is actually an average value of all the naturally occurring isotopes for carbon. First off, any question on the calculation there? Now, it is important to know that if you could like grab out and just pick up a carbon isotope, you would never find one that has a mass of 12.01. You would either pick up a carbon-12 isotope that has a mass of 12, or you would pick up like a carbon-13 isotope that has a mass of 13. So although we do use that as sort of the atomic mass for carbon, there really isn't an isotope of carbon that has that exact mass. It's really an average of all those naturally occurring isotopes together. So you would either grab one or the other in the case of carbon. Any questions on that? All right, I tried one, you try one. All right, bromine has 2 stable isotopes. A little bromine 79 occurs about 50% of the time. Bromine 81, 49% of the time. If the atomic masses of each of those isotopes are 78.92 for the 79 bromine and 80.92 for the bromine 81, what is the atomic mass? I'm assuming the right answer hopefully is up there. Okay, let's take a look. And obviously we have some isotopes given to us. It's usually a good idea just to make sure, take the percentages of each of them. And again, they should add up to about 100%. May not be perfect like it is not here as well. Maybe it'll just slightly over 100 or just slightly under 100, but it should be in that 100% ballpark. So in this case, we know we're not really missing any isotopes. Clearly, if we added the percentages up, and we only got to like 70%, we're probably missing another isotope somewhere, and there would probably be some more information given to you. So we want to use our formula where we're going to basically just take the first isotope plus the second isotope and do our percentages. So taking our first isotope, the 79, I am going to move the decimal place 2 places to the left, which will convert my percentage into a decimal. Again, you could divide by 100 if you would rather do that. We're going to times it by the atomic mass of our first isotope, which is 7892 AMU. Again, we're going to add it to our second isotope. So again, this represents basically bromine 79. We've got again, if you don't want to move the decimal, once again, you could just divide that by 100% and it will do it for you. And then you could times it by the atomic mass of that guy, 8092 AMU. And that would represent our bromine 81 and a little 7992 action happening there, I think. It's like this guy right out there, yeah. And that's pretty close to what we see on the periodic table, about 7990 for bromine. But again, it's not perfect. The percentages aren't perfectly 100, so might be a slight difference in an experimental type situation. Any questions on how to calculate atomic mass? Yeah. Yeah, I really wasn't looking on this one, to be truthfully honest with you, but in most cases, like we were talking about a second ago, when you do kind of pull off the atomic mass and stuff like that, usually 4 significant figures is kind of where you would want to leave it. So it'd probably be okay if you just kind of went with 4 significant figures. And in this particular case, we're multiplying and then we're adding. So we would go to decimal places. So we might actually end up with the same number of decimal places at the end. Okay. Other questions? Yeah. Yeah. If it works, if you know how to punch it in correctly on your calculator, you can. So I would just say if you know how to use that button correctly, then you can, yeah. Probably safer just to move the decimal or divide by 100 just to make sure that you're actually punching in your calculator correctly. Other questions? Okay. Then continuing on our journey here, we'll talk here officially about the periodic table. That's the periodic table. Looks great. Good talk. All right. So the periodic table is obviously an arrangement of all the elements where, you know, they were put together based on similar sort of properties. They did a really good job. They left, you know, space to fill in other elements along the way. But first couple of things is groups are family. If you're really old like me, nobody uses family too much anymore, but most of the people call them groups. And groups are basically kind of up and down in a column here on the periodic table. Depending on your periodic table, you might see a lot of different sort of numbering happening. For example, there is the A numbering. Some periodic tables have the B numbering. Some periodic tables just run 1 through 18, no A or B sort of numbering. This one has all 3 of those, I think, on it. So when we talk about groups, we typically use in this class and pretty much any chemistry class that you take, what is referred to as the A numbering, and that is sometimes referred to as the representative numbering. And what that means is group number 1 is right about there. It actually starts with lithium, by the way. We'll talk why that is in a second, but it actually starts with lithium. Group number 2 is right next door. We actually skip the middle part. Group number 3 is right there. That's group number 4. That's group number 5. That's group number 6, group number 7, and group number 8. I would say most people kind of leave off the A part of it. They don't really call it. Most people 1A or 2A. They just go group 1 or group 2, and that's personally how I do it. But it technically is group 1A, group 2A, and so forth. So that is the proper way that we will look at groups. And again, it's going obviously up and down in those columns. Going left to right on the periodic table is what is referred to as a period, heading in that direction. And it would be going this way are periods. And as you can see from this periodic table, maybe, there are 7 different periods going from left to right there on the periodic table. As we talked about previously, our number that we find above the symbol is our atomic number, which again is still our number of protons there are in the atom. Now, the periodic table is really broken up into 3 different sort of categories. There are metals, there are non-metals, and there are metalloids, which are also sometimes called semi-metals. Usually on most periodic tables, this is like boron up here. There's usually this like staircase sort of written in. You can kind of see it on there. Somebody got the red Sharpie up there and wrote it up there. There's this kind of staircase that comes down. And usually to the left of the staircase is where we find metals. Also, the two rows on the bottom are actually metals as well. So on the bottom here, there's a couple of rows. Those guys are metals as well. To the upper right of the staircase are nonmetals, and on the staircase there are metalloids. Now, metals are good conductors of heat and electricity. They also can be hammered into thin sheets. They have shiny appearances. Pretty much all metals are a solid at room temperature, except for our friend mercury, which on a lot of periodic tables, which is Hg, will be some different color, like blue kind of writing and stuff like that. Now, nonmetals, on the other hand, are a little bit different. Nonmetals have basically the opposite characteristics of metals. They're bad conductors of heat and electricity. They're dull, they're brittle. They also have a much more varied state than metals. Some of them are gases, some of them are liquids, some of them are solids. So you got a wide variety of them. Our nonmetals also are those diatomic molecules and elements of how they naturally come. So this is hydrogen right here. And that's like lithium. Hydrogen is what type of element? Is it a metal, non-metal, metal? It's a non-metal, right? Lithium and everybody below lithium is which is why hydrogen is not part of group 1. Yeah, so hydrogen is actually a non-metal, even though it's hanging out with all the metals over there, and that's because hydrogen has some unusual characteristics, which in some cases it acts very much like a metal, but it's actually a non-metal, and that's why, again, group 1 actually starts with lithium and not hydrogen. Again, if you're old like me, older periodic tables used to put hydrogen actually on both sides of the periodic table. You would find another hydrogen hanging out over there by helium, and you would actually have it on both sides. But hydrogen is actually a non-metal, not part of group 1, and not a metal, because everybody else basically in group 1 is a metal. So a lot of these nonmetals are those diatomic molecules like H2O2, N2, or F2, Cl2, Br2, I2. These again are those diatomic molecules, but are still elements, right? That's how they naturally come, as they come as twos. And most of those are gases, and some of them are liquid with some vapor happening over it. A metalloid is also referred to as a semi-metal, and metalloids have properties that are basically on both sides. So the same element that's a metalloid could have some properties that are very similar to what we see with metals, and the same element can have some properties that are very similar to what we see with nonmetals, which is why they're sometimes referred to as semiconductors in that area there, and that's where they're kind of sitting between the two, right? You can see boron sometimes included with metalloids in some books. I don't remember if yours does or not. I think yours doesn't, probably. And if not, then it's considered more of a non-metal in that particular case. Yeah. No, that's just another name for metalloids. So sometimes semi-metals are the same thing as a metalloid. Nowadays, and books and stuff, they typically will use more, I think, the metalloid sort of name rather than semi-metals. But years ago, people would call them semi-metals. But now I think a lot of times books will use more metalloid than semi-metals, but they're referring to basically the same thing. Yeah, it does depend on the particular element that you would be dealing with as to the characteristics, because each of those elements can have some that may be shiny and some that may not be, and some may be semi-good conductors of electricity, which are they're sometimes semiconductors, right? So they have the ability to do that, but maybe not as good as, say, a metal, and better than a non-metal in terms of that. Other questions? Now, some groups do have special names. So starting over there at group 1, as we've just talked about with our friend lithium going down, that is the alkali metals. Right next door, beryllium, magnesium, calcium, strontium. That is the alkaline earth metals. The word alkaline means basic. The word alkaline means basic, and that is where we get a lot of our strong bases from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. Basically, take any of those metals and throw a hydroxide, which is OH, onto it. You have like a base. This basically happens in that case. Skipping the middle part there, heading over to group 7 here, which is all of our halogens here. So that is our fluorine, chlorine, bromine, iodine, and group 8, which is right next door, is our noble gases, our helium, neon, argon, krypton, all the ons, xenon, and there is our noble gases in group number 8. Noble gases are sometimes referred to as rare gases. Noble gases means that they are set apart. They are chemically inert, which means they don't want to react. They're not interested in reacting. They're actually perfectly happy the way they are. They'll react with themselves, but not other things. And as we'll talk about when we talk about bonding, pretty much the whole point of all bonding is for everybody to become like noble gases and be very happy with themselves and not very reactive and very stable. So noble gases are very stable because they're not looking to react. So they're not looking to gain electrons, lose electrons, share electrons. They're just really happy with the amount of electrons that they got going on. The 2 rows on the bottom are set aside not to make the periodic table too big. If you follow the atomic numbering here, that's 57, that's 72. This row right there should go right about there on the periodic table. And if you follow the numbering here, that's 89, 104. Number 90 should actually go right there. So these 2 rows right here should technically go right about there on the periodic table. They don't do it because your periodic table will be really wide and create a really wide textbook that they have to put in the cover. I've only seen one periodic table that does it, and it's on a wall like that. It takes the whole wall because they got all those rows in the middle and the rest of the periodic tables down the road. These are the lanthanized and actinized because they follow those elements on the periodic table. That is essentially where they should be coming in. I guess the good news is we don't deal too much with them. Those are where a lot of radioactive elements are, some nuclear chemistry that we're not going to talk about in this class. But it's also where a lot of man-made elements come into play, like Einsteinium, Californium, and all those type of ones that have the nice names are down here. So we won't deal too much with that. Probably the only element you really should worry about in terms of naming is uranium. That does pop up, which is the U. That does pop up the most, probably not too much of the other ones on those 2 rows. The transition metals are these metals that are found between group number 2 and group number 3 on the periodic table. So these guys right about here in blue. These are the transition metals, as we'll talk about when we talk about naming. Transition metals can have a variable type of charge. So the same guy can make different types of charges depending on the situation. The 2 rows at the bottom are also sometimes referred to as inner transition metals because technically they should go right there in the middle of the transition metals. So somebody says inner transition metals, they're the guys on the bottom. But transition metals is really that thing that's in the box that is between group number 2 and group number 3. And has special rules as to how we go about naming those. Any questions on that there? So you need to know, obviously, the periodic table. You need to know which way groups go, which way periods go. You need to know the special names where the alkaline metals are, the alkaline earth metals, the halogens, and the noble gases, where the transition metals are. Any questions on any of that periodic table stuff there? Now, we talked, I think, the other day about sort of symbols and elements. Now that we kind of have a periodic table up here, again, a lot of symbols and elements, in this region, you should definitely sort of get familiar with, up in this area, definitely a little bit in this area. And then coming through like here, and back that way is where we will see a lot of symbols and elements and symbols that you'll come across a lot. So those are sort of the ones that you should sort of know. Again, we probably won't deal with too much on the bottom other than, as I mentioned, uranium, and not too much happening in that area. We're not going to probably deal too much of symbols in that area. So kind of left, kind of upper right, and kind of towards the top right there in the middle is where a lot of symbols and stuff, as we talked about, learning the symbols and the names of the elements that go with it. is really helpful, especially when we get to the naming part. Okay, why don't we continue on here? So we're going to kind of change gears a little bit, and we're going to talk about modern atomic theory. And really what this is about electrons, sort of where they are in the atom, what happens when electrons sort of transition from one energy level to the next. So when we have electrons, say on a particular energy level, a lower energy level, say to a higher energy level, when those electrons go to a higher energy level, as we talked about pretty much in chemistry, things in the lower state of energy is really preferred. It's the most stable. So when things go to a higher state of energy, they really don't want to kind of be that way. They really want to kind of bring back down the overall energy. So what will typically happen is the electron will try to work its way back down to a lower state of energy. The result of that is, because there's conservation of energy, the atom will have to give off that energy in the form of light or a wave. And that is the wavelength. So this is sometimes referred to as a photon of light. And if that photon of light actually comes off with a wavelength that matches up to what's referred to as the visible part of the spectrum where we see color, we'll see some type of color. So if you've ever done a flame test, you stuck a flame on it, it's going to excite all the electrons and you'll see some different colors that happen. You probably did that maybe cooking pasta water. Yeah. So as it boils, maybe it overboils. When it overboils, if it hits the flame that's underneath it, if you got a gas stove top, right, you'll see the flame change color really quick, right? And that's the salt hitting the water, the flame, and the electrons getting excited, and you see actually a color change. Also fireworks, right? Where they launch fireworks and it explodes. There's elements in there, and all those electrons and those elements go crazy, and then they relax back down to lower states of energy, and we go, ooh, pretty purple, green, and all the different colors that we see as the fireworks basically explode. So when we have electrons transitioning from one energy level to the next, there's a certain exchange of energy that occurs. And it could fall somewhere in the, we'll go with this one, less pictures, what is known as the electromagnetic spectrum. And the electromagnetic spectrum has some different parts, but there is a couple things that's important to, I guess, understand, which is we could have a wave, and a wave is basically how energy moves through space. And a wave can have a wavelength, which is referred to as lambda, and that's between two sort of peaks or troughs in it. And there is a relationship between the wavelength and the frequency, which is how often a wave passes a particular point in a second, and the energy. So if we have a wave that has a longer wavelength, it will typically have a lower frequency, and that usually means it will be lower in energy. Now, if we have a wave that has a much smaller wavelength, like this, usually it will have a smaller wavelength, a higher frequency. It's like moving, quite quickly through space. And that usually is higher in energy. So smaller wavelengths is higher in energy, longer wavelengths is lower in energy. And as electrons transition, energy comes off, it could fall anywhere in this electromagnetic spectrum. So on this end, which is 10 to the fourth, that is a long wavelength, which means we're a little bit lower in energy on this side. Over here, this is 10 to the minus 12, which is a really small number, and that is a small wavelength and higher energy. So on the sort of longer wavelength, we have things like radio waves, which not too bad, they're not too much energy. As we continue to the left there, we hit things like microwaves, which has enough energy to spin your water molecules really fast in your pizza. And then it's cooked in like 3 minutes. It's good to go, right? If we go a little bit further to the left there, again, the wavelength getting smaller as we're going to the left on this picture. We have infrared, and that's typically where we kind of feel heat and energy sort of coming off. Then if we go to the left to one more spot there, that is the visible part of the spectrum. That is where we see colors. That is your commonly referred to as Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. So if the energy or the wavelength is coming off as a result of those electrons transitioning falls in the visible part of the spectrum, that's where we see colors. So again, back to the fireworks example, they have lots of electrons transitioning that gives off wavelengths in this region, and we see different colors as they are exploding around us. Going to the left, the wavelength gets smaller. We have the ultraviolet part, or the UV part of the spectrum. That's why we put sunblock on, right, when we go outside, so we don't get too burnt or anything like that, because it's pretty high energy. To the left is X-rays, which is why they throw a lead vest on you, right? And they leave the room when they shoot the X-rays usually, right? They don't stay there. It's quite high in energy. And all the way at the other end, where we have the really smallest wavelength, are gamma rays. And gamma rays are, as we talked a little bit about, I think last time, kind of equivalent to like a neutron. It has no charge, but it's kind of just like pure energy. You definitely don't want to be in the room with that going off without protection. So gamma rays very, very high in energy. So even colors that we see have differences in energy. So on that side, that's like 700 nanometers. And on this side, it's like 400 nanometers. Red would be higher or lower energy than, say, purple or violet. Red is a longer wavelength, which means it is actually lower in energy than we have over here at violet. So if we're talking about electrons moving from one energy level to the next, because that is lower in energy red, when we see a red color, it could just be a transition of an electron from like one energy level to the next, not a very big jump in energy. We see some purple color happening. That could be like an electron going from multiple energy levels, which will take a lot more energy to do that transition. And that results in something like a purple kind of color being seen. Any questions on that there? Yeah.
Is that kind of related
I'm not 100% sure on that. You will have distinct colors depending on what metals are there. So if you did a flame test, my class just did it like last class I just taught. But if you do flame tests of different things like say sodium, potassium, calcium, for example, we put calcium in there, you'll see it kind of turn reddish. And if you do sodium, it'll be yellowish like you see when like your water over boils on the flame. Potassium is more purple and stuff like that, but it has to do really with the electrons and those electrons transition as to what colors you see. But every element will have sort of like a unique-ish type color that will give off something in the visible part spectrum. Not all electrons that are transitioning from different energy levels will actually give off energy or waves that fall in this region. So it may actually fall outside the region. So if the wave or energy that's coming off is like in the infrared part of the spectrum or like the UV part of the spectrum, you wouldn't see any color associated with it because there's no color outside of that sort of visible part of the spectrum. Other questions? Yeah. So identify the form electromagnetic radiation has the greater energy. So we just looked at it there. Yellow is closer to red, which means it has a longer wavelength than blue, which means blue has a shorter wavelength, should have a higher energy. Ultraviolet and infrared. So again, ultraviolet was after the visible part of the spectrum, which means the wavelength is getting smaller, right? So that should be more energy. And X-rays and microwaves, I'm going to go with X-rays on that one, going to be higher in energy in that particular case. Again, on that last chart we were looking at, as you went to the left there, the wavelength was getting smaller. Now, one common thing that elements do, and it's the idea of how electrons transition from one energy level to the next. And it's the idea of what is sometimes referred to as quantized energy, as we'll see in just a second. And basically what quantized energy means is electrons will transition if these are different energy levels, completely to one energy level or the next. They will gain or lose enough energy to completely make that transition. So you can equate it to like when you walk stairs, I think. So typically when we walk stairs, right, we have enough energy to get to this step, right, or this step, or that step. We typically don't walk the stairs and go, well, I'm just going to rest right there between the two steps, right? Because that's not going to end well for us, right? And that is how electrons really transition in this quantized manner. They gain or lose enough energy to completely transition from one energy level to the next. They will never find themselves just kind of hanging out between a couple of energy levels or something like that. And just like people, when they walk stairs, some people do one step at a time, right? Some people have enough energy maybe to do two steps at a time, maybe three steps at a time, 4 steps at a time. But electrons can transition like that as well. Some will gain or lose enough energy to go one energy level. Some can go down a couple of energy levels or up a couple of energy levels, but they will always gain enough energy to make that transition completely from one to the next. And the result of that is when we would look at, say, an element and you excite the electrons, which is sometimes referred to as a gas discharge tube, or that goes through here. If you looked at it through a prism, what will actually happen because of these quantized jumps in energy, you will get what is referred to as a line spectrum. And a line spectrum means that a particular element, as those electrons are transitioning, will give distinct lines with distinct colors at specific wavelengths. And again, we may see a red line that would be maybe a nice short transition, as opposed to, say, the more purple line that we see there, that is a result of multiple energy levels happening. Elements are so unique that every element has a unique line spectrum. So by what colors you see in the line spectrum, what wavelength they come out at, you can actually make a good prediction as to what element you're looking at. They are so sort of unique in that sense. Now, energy levels are what are referred to as N, and N is the principal quantum number. And that is a fancy word for N, I suppose. But that's really a fancy word for energy level. And there is N equals 1, which is the ground state. That is the lowest in energy. And that is the closest to the nucleus. Anything above that, N equals like 2 through 7, is excited states. Higher in energy, further away from the nucleus. So N equals 1 is the closest you can get to the nucleus, the lowest in energy. And as you go up 2, 3, 4, those are higher energy levels. As we'll talk about, electrons go into the atom, like we walk stairs, sort of lowest one first. Yeah, so it goes lowest energy, then to the next lowest energy, and then the next lowest energy. And they fill up basically all of those things from lowest energy to highest energy until all the electrons are basically in there. So as I was mentioning before, just a second ago, that's the idea of quantized energy, these different energy levels, and these electrons transitioning. Now the sun, for example, is different than like elements. Sun gives off what is referred to as a continuous spectrum, where everything comes off at once. You got heat, you got all the different wavelengths. So a continuous spectrum, different than a line spectrum, is kind of like when you walk up a ramp. You could literally stop anywhere along the way, right? And that's what could happen in a continuous spectrum like the sun, gives off heat, light, all things coming off all at once. While electrons in elements, they transition very discretely from one energy level to the next, and you get these very discrete lines that come off. All right. By the way, when we talk about emission spectrums or spectrums in general, there's two types. There's an absorption spectrum and an emission spectrum. So when an electron goes from a lower energy level to a higher energy level, it needs to absorb energy. And that is what is referred to as an absorption spectrum. It actually has to gain energy to do that. The only way that electron could go from a lower state of energy to a higher state of energy is it has to gain energy. And that's what you do when you do like a flame test, right? If you put it in a flame, it just gained a lot of energy. If you turn on an electrical discharge tube, which is like an electrical current running through it, that's going to excite all the electrons. There's a lot of energy, and you'll get a certain type of emission spectrum, or a spectrum, which is known as an absorption spectrum. An emission spectrum, or something that gets emitted, is when an electron goes really in sort of the opposite direction. It starts at a higher energy level and comes down. So it's got to give off the energy to do that. And that's what is sometimes referred to as emission spectrum. Most of the time when we see colors like, those type of things, fireworks and flame tests, those are emission spectrums because those electrons are coming back down in energy. They're releasing that energy and we see the different colors. The absorption part of it would be when it actually stick it into the fire at the beginning and it gains like the energy and it goes upwards. So anything that goes from lower energy to higher energy in terms of electrons has to absorb energy. Anything that goes from a higher energy level to a lower energy has to emit or release the energy to allow those electrons to come back down. All right, so absorbed, emitted, or node change. If an electron moves from the first energy level to the third, so we're going from lower energy to higher, are we absorbing or emitting energy? We got to absorb energy to do that. Electron goes from the third energy level to the second. It's now dropping energy levels, right? Coming lower in energy. So it would have to emit the energy. An electron moves within the same energy level. Yeah, no change because it hasn't really transitioned. So again, if it chooses to transition or it will transition, it will definitely gain or lose enough to make the transition. So just moving around the same energy level will not result in any type of absorption or emission that will happen in that case. All right, so we talked about the ground state and the excited state. So when we look at an atom and where electrons are in an atom, are what are referred to as orbitals. So an early idea of sort of how electrons are in the atom was one that was done by a guy named Bohr. And it's sometimes what is referred to as the planetary model, where you have your nucleus and you have these orbits. You have these electrons that are prettily moving around in circles. They absolutely do not do that, by the way. So this type of model where we know for sure, like if I put my finger on that orbit, it's going to come around and hit me, is not how electrons move. So we moved away from this Bohr model, the planet model, where we don't use orbits, and more of a theoretical sort of model where the best that we could say is there's a really high probability of finding an electron in a particular location within the atom. That means I don't really know how it got there. I don't really know how it's traveling. And the idea of the more you know how an electron is traveling, the less you know about exactly where it's at, and vice versa. The more you know about where it's at, the less you know about how it's traveling. They call that the Heisenberg uncertainty principle. Yeah? Also known as Breaking Bad now, but it moves around. So the idea is we really don't know how a particle like an electron is moving. And the best we could do is go, I think there's a really high probability of finding an electron in this part of the atom. And we would know just by thinking about it logically that, near the nucleus should be a pretty high probability, right? The nucleus is positively charged, electrons are negatively charged. So again, we're going to have that attractive force between the two, and it should be a pretty good probability of finding the electrons located there. As we move out from there, the probability gets less and less. And again, even close to the nucleus, we still don't know exactly where it's at or how it's traveling. And again, it's moving really randomly about it. So they moved away from the idea of orbits to this idea of orbitals, which are really just probability maps. And there's different types of orbitals, but a couple of things about the orbitals. Any individual orbital can hold 2 maximum electrons, or 2 electrons maximum, I guess a better way to put that is 2 electrons maximum. And there are some different orbitals. There are s orbitals, which look like this. This is basically a sphere. And we actually find s orbitals on every energy level. So they actually start at the very first energy level, the n equals 1 level, the lowest energy level, you will find s orbitals. You will also find them in every single energy level past that as well. When we get to p orbitals, there's actually 3 different types of p orbitals, and they start on the second energy level. So on the second energy level is where p orbitals happen. On the first energy level, we have what is referred to as a 1s orbital, basically just 1 over. On the second energy level, we have a 2s orbital. The 2 means it's on the second energy level and it's an s orbital. And that is where we first start to see p orbitals occur. There's actually 3 different types of p orbitals, and that is referred to as a p subshell. The 3 different types of p orbitals is a px, a py, and a pz orbital. Basically, it is the different orientation in 3-dimensional space, like on the x, y, and z axis, if you're graphing something. On the third energy level, that is where we start to see d orbitals actually occur. So on the third energy level, we still have s's, we still have p's, but this is where we start to see the d's first to occur. And actually for d orbitals, there's actually 5 different d orbitals. And when we get to the fourth energy level, that is where we first start to see the f orbitals, which look like that in the box. I'll come up here. On the fourth energy level, we still have the s, we still have the p, we still have the d. I ran out of room, but I'll come underneath, but it's actually the same energy. And that is where we first start to see the f orbitals, if each of those lines represents an individual orbital. So when we talk about s orbitals, there's only one type that could hold a maximum of 2 electrons. Like I put 2 electrons, if those arrows are electrons in my s orbital, that's it, it's full at that point. P, there are 3 different types of p orbitals. And that means it could hold a maximum of, if each one could hold 2 and there's 3 of them, that is a maximum of 6 electrons if you filled up the p subshell. And this would be like our p subshell. This guy could hold 1 and 2 each. So each of those could hold 2 electrons. Again, if those arrows are electrons and the lines are individual p orbitals. All together, these 3 individual p orbitals are what are referred to as a subshell or a sublevel, depending on your book. So all 3 of them together is a subshell, or some books use a sublevel to talk about it. Now, the d orbitals, there are 5 different types of d orbitals, which means if we filled up all 5 of those d orbitals, that is 10 electrons we could throw in there. Which would be somewhere around here. I run out of room, but we put them all in there. That's not how they actually go in, but we'll just fill them up with some electrons. You would have 10 electrons. And if you took all 5 of these d orbitals together, that would be what is considered a 3D subshell or sublevel, all 5 of them together on a particular energy level. And if we get to our f orbitals, there are 7 different types of f orbitals. And that means you can max out at 14 electrons if you fill them all up. So if I put electrons in each of those 7 orbitals there, 7 times 2 is 14 electrons. And that would be all 7 of them together is the F subshell. Question on that. So those numbers are actually really important when we write electron configuration. How many electrons you can put in an s, and it's only really called an s orbital because there's only one type, so it's just an s orbital. P, there are 3 of them together, which gives us a p subshell that could hold a maximum of 6. You don't necessarily have to put 6 in there, but it could hold only a maximum of 6. D, there are 5 different types, could hold a maximum of 10 electrons. Once again, you don't need to fill all 10 up, but the maximum it can hold is 10. And there are 7 different f orbitals, which each one can hold 2, which gives us a total of 14 if we fill them all up. And again, you don't need to fill them all up, but you could if you needed to. You could think of the orbitals as like, you could think of it like a hotel, I guess, or something like that, if you like. You go to a certain floor, that would be like your energy level, right? When you get off the elevator, there's different rooms on that floor, right? Those are like different orbitals, right? And if you go into a room, maybe it's a nice room, there's a couple of different rooms inside there. So maybe there's more than one orbital in that subshell room. And that's where the electrons are sort of hanging out. So here are the different p orbitals. And like I said, px, py, and pz. It's really just the orientation in three-dimensional space. For our purposes, you don't have to worry too much about that. By the way, these are, again, theoretical probability maps. There's really not circles and figure eights and donut-looking things and atoms, but they're just really probability areas within the atom of where you would find an electron. You kind of think of like in the middle there is kind of like the nucleus. And so near there on each of those things is where the electron can be housed. So when we have only one electron involved, which is hydrogen, we can see that all the orbitals are equal in terms of energy. And what I mean by that is this would be like your n equals 1 level, your n equals 2, your n equals 3, your n equals 4. So everybody on the third energy level is equal in energy. Everybody on the second is equal in energy. By the way, just a couple of questions before we move on from that. How many electrons can I put in there to max out the n equals 2 level or shell? How many electrons if I max out the n equals 2 level or shell? Yeah. So n equals 2 level or shell means any orbital that is sitting on that particular energy level. So that would be all those guys there, which I think I heard the correct answer. This guy could hold 2, right? 4, 6, and 8 electrons if you max out the entire level. So sometimes, much like subshell or sublevel, people call it shell or level, and it's referring to a particular energy level and all the orbitals that are on there. How many? So that would be 8 electrons if you maxed out. How many electrons if I maxed out the 3D subshell? How many electrons could I put in there if I maxed out? So 3D subshell means all the 3D orbitals and only the 3D orbitals that are on there. And that would be 2, 4, 6, 8, and 10 electrons. Yeah. So again, if I said the n equals 3 shell or level, how many electrons would that be? That would be your 18, which would be 10, 12, 14, 16, and 18. That would be everybody on there if we were talking about the n equals 3 level or shell. But since we're talking specifically about the 3D subshell, it is just 10. How many electrons in a 4p orbital? So this is 4p, yes? How many electrons if I max it out? The answer is 2. Orbitals could hold how many? Only 2. That's a trick question they have in your lab, probably. That could be this orbital could hold 2, right? We could be talking about that orbital that could hold 2. We could be talking about that orbital that could hold 2. If I said how many electrons in the 4p subshell, how many would it be? It would be 6 at that point. So if I said the 4p subshell, that's all of them together, and then it would be 6. Yeah. Any questions on any of that? Questions? Yeah. Yeah, so in this case, these lines represent, sometimes people use lines or boxes to represent individual orbitals. So they represent one individual orbital. So as we talked about, for example, where the 2p is, we talked about that there's 3 different types of p orbitals, and each one of those lines represents a different type of p orbital on that energy level. It's actually px, py, and the pz orbital. And that's, again, just how they are in sort of 3-dimensional space moving around. And each one of those individually could hold 2. Taken all those together would be the subshell or sublevel, which each one could hold 2, gets you 6 total if we filled up the entire subshell. Other questions on that? Okay, so back to the original picture there, which is And with one hydrogen electron present, everything's perfectly equal on all the energy levels. All the guys on the third energy level is equal in energy. All the guys on the fourth energy level is equal in energy. What happens when we get more than one electron, which is after hydrogen, is there's actually a shift in the energy. And that's what they look like, the orbitals, when we have more electrons involved. When we have more electrons involved, there's a lot more negatively charged. So it's kind of an earlier question. That means they really don't like to be near each other. So things are going to start moving around as you start building out a lot more electrons that have the same negative charge in there. And it, just to show you the difference, equal, different. That's going to affect the order at which electrons go into the atom. They always go lowest energy first, then the next lowest, then the next, then the next, and they keep going until they fill it up. The major difference is after I get to the 3p, it is actually the 4s comes first, and then we go back to the 3d. So there's a big switch in that, and that follows up here as well. We go to the 5s and then drop back to the 4d. So there is a change in the order at which they go in because of the presence of a bunch of electrons at once. Those orbitals actually shift energy levels, and it affects the filling order at which electrons go in. So there is a specific filling order that, frankly, you can make yourself. And I would highly recommend you learn how to make it yourself because it will help you write any electron configuration you need to do. You could remake this thing very easily by remembering basically what we just talked about. On the first energy level, the only orbital that is there is what type? An s orbital, right? So that's like a 1s, right? On the second energy level, that is where we start to see our p's happen, right? So we go 2p to the right of it. On the third energy level, that is where we see our d's start, right? And on the fourth energy level, that is where we see our f's start. Once you put those four down, you just go numbers underneath it with the same letters. So this would be 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 4f, 5f. So you could recreate that for yourself quite quickly by just remembering basically this and then fill in all the numbers underneath. Frankly, if you put too many numbers, you'd probably still be okay. I'll be honest with you. You know, if you put way too many numbers on some of them. So that's a really good way to know this. If you know this order, and you know that, as we just talked about, you can max out with 2 electrons in the s orbital. The p subshell is 6 electrons. The d subshell is 10 electrons. And the f subshell is 14 electrons. You could write any electron configuration you would need to write. How this works is you always start at the top and you basically just follow the arrows. Yeah. So you go to the end of the arrow, come back up and come back down, come back up. So you basically just keep zigzagging back and forth, and it will take you through the proper order for writing electron configuration. So let's take a look at electron configuration, how this works, and let me remake that again to show you how you can remake it pretty quickly. 1s, go down to the right, 2p, down to the right, 3d, down to the right, 4f, and now just fill in the numbers. So again, 2s, 3s, 4s, 5s, 6s, and 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And again, I just very quickly recreated that, and it's a very good thing. So let's take a look and see how we write electron configuration properly. Again, we're always going to start up here. So we'll start with our friend hydrogen, which is lucky number 1 on the periodic table. It has 1 proton, which means hydrogen that is neutral should have 1 electron as well. So we will start at the top and we will write the electron configuration as 1s1. And that is how you write it. There is no dashes, there's no big numbers. That is this first number is the energy level. and that is the principal quantum number. That's that n number. This is the orbital, our subshell that the electron is hanging out in, and the number on top, which should be a subscript or superscript, is the number of electrons in the orbital, our subshell. So let's take a look at helium. Again, I'm going to start at the top, and helium has 2 electrons. So starting at the top will still take me here first. And the electron configuration would be 1s2. The first one means I'm on the first energy level. The s means my electrons are hanging out in the s orbital. The 2 on top is how many electrons are in that particular orbital. Can I put any more electrons into that s orbital? I cannot, because it could hold a maximum of 2, and it is full at this point, right? If I have more electrons, I got to zigzag and come back through this way, right? To 2s next, right? And that happens at lithium. Lithium is the third 3 electrons. Again, we start at the top, which means 1s2. Now we zigzag back. The next place we're going is 2s. And how many electrons do I need to finish it there? Just 1 more in there, right? If I count the top numbers, I got 2 and 1, which is 3. That is the total number of electrons that I should have. I have how many electrons on the first energy level? 2. How many electrons on the second energy level? 1, yes. And I know that's the second energy level because that's a 2, right? So that is basically the n equals 2 level that we are at now with our electrons. Question on that there? Yeah. Yeah, so this is electron configuration, which is basically telling people how many electrons there are and where they are found in the atom. And it's what is sometimes referred to as the filling order, how they go into the atom and basically where they end up. So you should end up with an electron configuration that has the same number of electrons as whatever you're writing it for. Yeah. Other questions? Now let's do it. I got time, you got time, it's beryllium, right? What should the electron configuration be for beryllium? We're going to start at the top again. So we should start with 1s2. Next should be 2s2, right? Can I put any more electrons in that second s orbital? No, it is now full, right? Which means, again, if I have more electrons, I need to continue on. I now have how many electrons on the second energy level? I have 2, right? And on the first, I still have 2, right? Grand total of 4 electrons have found a home. And you're going to ask what happens when we go to 5. Well, let's do it. Let's go to 5. That's what I'm saying. You know, I'm here to answer your question. So let's go with boron. Boron is 5. So let's see what we should do. We should start up here again. So we're definitely going to roll with 1s2. We're going to zigzag back here to my 2s, which will give me 2s2. So that is 4. I now should zigzag back up here to 2p, and I will need a 2p1. Yes. I count up the top numbers. I got 2, 2, and 1 is 5. So I have now placed 5 electrons. Number of electrons on the second energy level is how many? N equals 2. How many electrons we got there? It's actually 3. That is a 2, and that's a 2. That's 3 electrons on the second energy level. On the first energy level, we still only have, and we only have 2 because that's the only orbital on that energy level, right? So you can't have any more than that in this case. By the way, that is the p subshell, right? If I want to fill it up with more electrons, how many more can I put in there before it's filled? 5 more before it's filled. So we're not going to move off of that spot until we pop in there 5 more. I know your question is we should do that. I agree. So let's go to carbon next, which is number 6 on the periodic table. And we will again start at the top, which will be 1s2, 2s2, and again zigzagging back into here, we should end up with 2p2. Yeah. Again, counting the top number, we have 2, 4, and 6. We now have how many electrons on the second energy level? It is 4 at this point, right? And still 2 on the first. So what's happening at this point, if we were to draw our little boxes to represent our orbitals, not drawn correctly in terms of energy, but what is happening actually at this point is the first electron is going into the 1s, and then the second one actually goes in an opposite direction outside the scope of our class. The next one goes in upwards direction, and this one gets filled in. And by the way, that's how they go in. First one goes up, the second one goes down. We actually have a bunch of 3 different orbitals here. How they actually go into these orbitals is they actually do go in one at a time. Yeah, so they actually will go into individual p orbitals one at a time before they then come back and kind of pair up. It's a rule that's known as Hund's rule, which is, again, not worry about our class, but that's how they go in there. But we could clearly see we still have 2 more that we could put at the end, right? And 2 more at the first 2. So we still have 4 more spots to it. So might as well finish it out here. Nitrogen, which is 7, should have an electron configuration of 1s2, 2s2, and 2p what? 3 in this case, yeah? The third electron, by the way, for nitrogen would actually end up here if I steal the little diagram here. They now have 1 electron in each of the p orbitals in that subshell. At this point, they have no choice but to come back actually and pair up with each other. And that happens when we get to oxygen, which is number 8. It will be 1s2, 2s2, 2p4. Using the same diagram up here, what happens now is that 4th electron will pair up. That p orbital now on the left there. Can I put any more in there? Can I put any more electrons in this p orbital? No, it's full, right? So the other electrons would go into the other ones, and might as well finish the first 10 here, which is fluorine, which is number 9, which would be 1s2, 2s2, 2p5. How many electrons on the second energy level? 7, yes, 2 and 5. The 5th electron would go into that middle one, which will now fill up the middle orbital, leaving us just that last orbital, which is actually the pz orbital with 1 more spot for an electron. And you don't have to ask, we'll do it. Neon, which is 10, which will give us 1s2, 2s2, 2p6 in this case. And that will then fill up that last orbital on that energy level. And we now have lucky number 8 there on that energy level. And we have 2 on the lower energy level. This is the way you should write electron configuration. It should look like that, 1s2, 2s2, and so forth. There are no dashes, as you see, yes, no commas, no 1s2 dash, 2s2, none of that weirdness. Yes, so do that. Your lab manual used to be really bad. She used to just use numbers for electron configuration, like 2, 4, 6, 8. Who do we appreciate? Yes, don't do that. For lecture, I don't know what he wants for lab, but for lecture, this is how you should write electron configuration. That's really the proper way. Any questions on that? All right, let's